So welcome everybody to today's data-centric engineering webinar. Today we're really pleased to welcome Professor Ron Kenett, who's going to be presenting engineering emulators, digital twins, and performance engineering. If you don't already know what data-centric engineering is, we're an open access journal, which is published by Cambridge University Press. And we'd like to thank our editors and also the support of the Lloyd's Register Foundation and the Alan Turing Institute. Now, before we get started, just a quick reminder about the current calls for papers that we have. So we're there upon the screen now with a few updated deadlines as well. A couple of deadlines have been extended there at the request of some authors that are contributing. If you'd like to know any more, please just visit the website. The information there is updated regularly, and you can get a bit more information on how to submit and what kind of things you need to know beforehand. Okay, so back to the main thing of today. So again, we're pleased to welcome Ron Kenett. Now, Ron Kenett is a senior research fellow at the Samuel Neiman Institute in Israel. And he is the chairman of the KPA group and of the Data Science Society at AEAI. He's also a research professor at the University of Turin, as well as having published and been an author or a co-author on over 250 papers and 18 books on data science, industrial statistics, biostatistics, healthcare, customer surveys, multivariate quality control, risk management, system and software testing, and information quality. So if that doesn't help explain to you how breadth this man's knowledge is, then maybe the rest can do it throughout the presentation. He's a member of many advisory boards, including the Council for Statistics in Israel, the Digital Twin Center of Excellence, the Informs QSR, and the University of Haifa Data Science Research Center. Now, before we get started, I'll quickly point out how the Q&A works. So at the bottom of the screen, you'll have a Q&A as well as the chat function. We'd like to recommend you to use the Q&A during the presentation. So those questions will be in there. And then at the end, we can read them out to Professor Kenett. So please just, as soon as you have a question, put it in there whilst it's still on your brain, whilst it's nice and fresh. We can thank the modern technology now for not having to scribble it on the paper and then can't really remember what you were thinking. So yeah, we'll be taking some time to answer those at the end. If you do have any problems, any technical issues, please post it in the chat box and one of the members of the team will help sort that out. So now I would like to hand over to Professor Kenett. So Professor Kenett, whenever you are ready.
I am. You have to let me share the screen. I can. Okay, very good.
There we go.
Okay, hello everyone. I look forward to this, the opportunity to present insights gathered through many years of experience and the hopeful conversation and discussion that will follow that. So this list is long because the focus of the talk is on insights that are I would say conceptual. It's not a technical talk. There is only one slide with formulas, and therefore it's about ideas and observations. Okay, now it's stuck. Why is it stuck? So the elevator pitch, the talk that you give, the brief talk that you give to people who have 3 minutes of attention. The engineering community, the engineering sciences have focused on design. And once a system, a product is designed, it is shoved over to manufacturing, who is assembling it, and then it's moved to customers who are using that. The main point in this talk is that we are undergoing a major shift in this paradigm. And instead of engineering the design, we see more and more of engineering the performance. And the talk is about what engineering the performance is about. The main reason is that we now have a lot of sensor technology. We have vibration sensors, we have scanners, we have displacement sensors, and we can do a lot with those. So the talk is about moving from engineering of the design to engineering the performance. What does it mean? The first thing, it means that nominal engineering is the past, and that has implications on contractual requirements, on architectural design, on system design, on scheduled maintenance. Now, what we see is a different perspective, which integrates sensors, IoTs, with systems, which models faults, has enhanced monitoring, diagnostics and prediction, and this is packaged in digital twins. This requires a life cycle view, so you have to look at the system from a wide perspective. And instead of scheduled maintenance, you are aiming at condition-based maintenance. So there are specific changes that go with engineering the performance. The bridge is, I think, where we are now, and that's where the challenges are. So some background. We have an understanding of physics, so we can draw through differential equations and partial differential equations the behavior of a system, and we will observe a discrepancy between the real thing and the models, which reflect some knowledge gap. In fact, what we are subjected to is poor precision. If we use the data coming from the sensors, if we are taking a data-driven perspective, on the data points, we will have the exact behavior of the system. The system behaved as observed in the data point. The difficulty will be in the generalization of the understanding. What happens between these data points? So physics gives us an understanding, data gives us an understanding, and the challenge is to merge these two types of understandings. The way I present it is by showing these three planets. In fact, we are taking a journey through three planets. It's planets of the theory, Navier-Stokes equations, hydrodynamics, Newton, statistical inference, Bayesian analysis. This is all in the theoretical planet. We take a trip to the planet of the needs. We need to control systems. We want systems that will operate without failure. We want to act on the systems when the chance of failure is increased, whereby we introduce condition-based maintenance. And then there's a third big planet, which is the delivery planet. If we have the theory and the needs, we need a delivery platform. So the delivery platform, which can be Python code or R code or other statistical platforms, will allow us to bridge the theory, the need, and provide added value to users, to customers. So the life cycle view I mentioned is from problem elicitation, what's the problem, to goal formulation, which is where we are able to translate the problem into metrics. We then collect data to compute these metrics. We do some data analysis, we formulate findings, we operationalize the findings, we communicate the findings, and we do an impact assessment. So this is what I meant by life cycle. There is a reference here if someone's interested, and the link to the paper that you can download. That's the journey from a process perspective. So what do we mean? What do I mean by engineering the performance? There are 4 analytic capabilities which help focus the discussion on performance engineering: monitoring, diagnostics, prognostics, and prescriptive analytics. So the sensors and the cyber-physical systems with the analytics provide us the ability to have these 4 capabilities. The systems that we observe now, in chapter 1 of this edited book that we published a couple of years ago, we talk about porous systems, are full of holes. So the requirements are not complete because we expect some unusual behavior of the systems. Through the sensors, we will have a layer that is able to handle this unusual behavior. And these systems are therefore not fully designed. By designed, I mean they don't have all the requirements completely laid out. And that's what we call porous systems. To handle this level of uncertainty, the digital twins are providing the capabilities that I just mentioned. So we have the physical systems. Here we talk about the cyber-physical system, the raw material that is the input to the system, that is used by the system, the measurement devices that are around the system. We have the outputs. These are all tangibles. These are the physical assets. And the digital assets, which is what happens on the digital space, which is where the digital twin comes up. The digital twin, in that sense, is not a simulator because it's fed online by sensors. So a lot of people talk about digital twins referring to simulators. In the way I present it here, simulators, if they are hooked online to operating systems, then they can form digital twins. If they are done offline, they are not part of a digital twin that is used to manage a system. So that's the difference. And sometimes the terminology is a bit mixed up. What we can handle as a result of all this is the engineering of performance, is to handle uncertainty. What do we mean by uncertainty? So uncertainty means the validation, which is the comparison of what the model says and reality, that needs to be treated, and that's where statistics and data science methods are coming in. And to make this validation worthwhile, we must trust the data, we must trust the model, and the trust is based on what we know that is happening. So this is not something that can be automated. At least my opinion is that these things cannot be automated. But the uncertainty evaluation gives us a better understanding of the level of trust that can be placed in model results. In preparing for this webinar, I looked at previous webinars. One of them I recommend is by Gianluca Iaccarino from Stanford. He talks about fluid simulations of fluid, CFD simulations, and to include uncertainty in the model, which generates phenomena that are observed and of interest, that without the uncertainty are not observed in the model, so therefore the validation is poor. He introduces a mix of shapes, and you can see on the bottom right the different types of shapes that go through this simulation. When you do that, then you observe something that is in the simulation that is also apparent in reality. So this is not a digital twin, it's a simulation of a process of turbulent flow. And computational fluid dynamics are a very well-established technology, and I will mention how we can incorporate that in digital twins in later slides. Another type of models that are used extensively, especially mechanical engineers are specialists in this, are finite element methods. So let's say you take a parking brake, you want to simulate the loadings on this platform. You discretize it, and then with knowledge from physics on differential equations, you can model what happens to these elements, to these nodes, and get some model of what happens to the system when it operates. These finite elements can be one-dimensional, two-dimensional, three-dimensional. An excellent review of this, which distinguishes the real system that is modeled and operates with the finite element models from where you observe data. So you observe data both from the real system and the finite element methods, and the data is affected by noise, is in this YouTube presentation. The modeling here is based on modeling finite elements, and the seminal paper that is discussing misspecified models and uncertainty is by Mark Girolami, and that's a paper that showed up in PNAS, and I think both the paper that I mentioned before. Oh, come on, now it's stuck. Namely, this paper on numerical simulation of flow around a circular cylinder by Gianluca and colleagues, and this paper by Mark and colleagues are worth reading. They give you a full picture of how engineering tools aiming at simulations can be used when you want to account for uncertainty. I have developed, this is based on work we did in 2006 in the context of a European framework program called TitoSim. We developed a stochastic emulator, and the idea, I will talk about the idea now, and then I will show you later an example, is that we have a model of a system. It can be a CFD model or FEM model or a physics-based model or an empirical model. We generate noise by introducing uncertainty in the inputs of the model. And then we emulate the variability. That's what the stochastic emulator is about. So we have two models. We have the model of the performance, and then we have the model of the uncertainty. And that allows us to optimize both on performance and robustness. So in this book on industrial statistics, we have a chapter on computer experiments where we discuss that. So this was a general background on performance engineering. Now I'll give you some examples you can consider more practical. 2 case studies. This is a case study of a locomotive parking brake. This was published in Scientific Reports a couple of months ago, actually. There are several other papers coming up from this work that is led by Gabriel Davidian, who is a PhD student at Ben Gurion University and is doing fantastic work. So we have a train, a locomotive, and there are systems on this train. So there's a safety valve, there's a suspension system, there's a brake system. The approach that was taken is to consider each of these systems separately and develop digital twins for the individual systems. So let's take a suspension system. Okay, there are failure states known to the suspension system. You just go through the data of the maintenance depot to figure out what are the failures. There is a lateral damper failure, a wheel flat failure, a spring failure, a combined spring and damper failure. So we know what failures occur. We have sensor data. What can we say from the sensor data that relates to these failures? And can we use the sensor data to diagnose the failure, to provide some prognostics on the failure, and initially to monitor the existence of such a failure? So on the suspension system, there is a mathematical model which describes the performance of this system. So we have basically mathematical equations. We have the FEM model that is applied to this suspension system on the left. On the right, we have a brake system. So this has been done on the 4 systems I mentioned before. Through the sensors, we have a picture that gives us a comparison of what is supposed to happen and what is happening. If what is happening is matching what is supposed to happen, we are okay. If there is a gap, that's when the system has to be looked at, and the prognostic model will tell us if this is urgent, it's a showstopper, or this can be looked at when the train gets to the station, or maybe during a monthly or weekly checkup schedule. So let's take an example. This is a wheel flat. A wheel flat is in trains. So trains have wheels. The wheel flat is not the flats that sorry, I didn't close my phone. So the flat is this, what you see here on the wheel, and this is a high risk to safety. The bigger the flat, the bigger the risk. So we have flats of size 10 millimeters, 20, 30, 40, 50. We've observed this type of flats. Okay. Now we have a sensor that is measuring vibration. How can we use the sensor that measures vibration to identify potential wheel flats, and also to tell us what is the extent of the failure? So the green is the nominal state. The orange is the wheel flat at 10 millimeters, and the red is is at 20 millimeters. We get these from a digital twin. The behavior of the sensor is derived from a digital twin. We can use, in this case, we use the neural network. Here's the framework for this neural network to get some predictive analytics based on the vibration sensor, on the fact that there is a wheel flat and the extent of the wheel flat. And I will show you now how it looks. So here's the, oh. So on the top, you see the sensor. This is a pressure sensor. On the bottom, you see the opening of the valve. You see the valve here. And this happens as the locomotive runs. So it's an online system. There is basically a control room where this type of information is pushed to. And the result is that you can avoid increased risk of failures during the running of the locomotive, and optimize maintenance, because you know how to schedule the maintenance activity accordingly. So this was an example of an operating system on a real system. Now I want to give you a few slides on what I call the pedagogical case study. It's a piston with 7 factors. It's part of the Python code in the book I mentioned before, in the MyStat Python code. You have all the links to download that, so you can use that. The same piston has been also developed in R and in Jump, in the Jump software. So we are tracking the performance of this piston, the cycle time. How long it takes for 1 revolution is the cycle time. We have 7 factors. And if you run the piston at the operating conditions, which are the standard operating conditions, we are going to observe variability in the cycle time. There is uncertainty behind this piston. There's a simulator that introduces uncertainty in the inputs. And you can see that the range of cycle time is between 0.755 to 0.78. And that's what happens under normal operating conditions. To analyze that and provide the monitoring capability, we can use a control chart. This is a X bar S control chart. This is aggregating 5 cycle times, consecutive cycle times, and the black dots are the averages. So we have 30 aggregations like that, samples. This is because we have 150 observations, and we put them in samples of size 5. The bottom chart, the companion chart, is the S chart, the standard deviation chart of the 5 aggregated measurements. And we can see that the process is stable. There is maybe 1 point which is touching the upper control limit for the standard deviation. So these 5s, which are here, have a slightly higher variability. overall, we have not changed anything, so we know that this is a system working under stable conditions. As we follow the behavior of the piston, we can see a drop. Okay, we can see a drop in cycle time. So the challenge for the students is figure out what can cause such a drop. Okay, this is an obvious drop. Why? Because we have a simulator, we can run computer experiments on the simulator. Here you have a space-filling Latin hypercube design. There are other types of design. This is done with the JUMP software platform. So we fill in the space. We fit a Gaussian model. This is a Gaussian process model, also called Kriging. So points which are close will have high covariance. Points which are distant will have low covariance. And the parameter theta is parameterizing the model. If we fit this model, we have the theta values. We can see that V0 and K are the two factors that affect cycle time. They have the highest main effect. In JUMP, you have a profiler. This is a prediction profiler that is dynamic. So you can move this dotted line left and right and see how it affects the cycle time. And the blue values indicate the confidence interval around the red value. So for this setup in the center location of the 7 factors, we have 0.9 with 0.74 to 1.06, 95% confidence interval. So V0 and K, they have a threshold. As we go below this threshold, then the cycle time drops. M and S have an effect. And T0 and T, which are the temperature, the ambient temperature, they seem to have no effect on cycle time. Okay, this can be done again if with either empirically with data or from perturbations on the FEM model or the CFD model. So you have a lot of options here. Once we have the performance model, which is what I showed you before, we can introduce variability in the inputs. Here I'm introducing variability in V0, K, M, and S. You see, this is what these distributions indicate. And I can now generate through another experiment on these inputs, I can generate the stochastic emulator. And on the top, you have the prediction profiler on the defects of the system, namely the rate of observations that are outside of specifications. If we use these two profilers together to optimize, so we model the response and the variability, it's like moving from 1, which is very bad performance, to 3, which is optimized only on response, to 2, sorry, to 3, which is a more robust, because once you are here, you can move and nothing happens. At the peak, any direction you move, you're going to drop. So the stochastic emulator is giving you a robust solution. And again, this is something you can do with whatever input you have for the original model. And this is a stochastic emulator that has also good computational performance and can be incorporated in a digital twin in a much easier way than a fluid dynamic model or a FEM model, which can take a lot of time in computation. So these ideas, these tools, these methods are new engineering practices. Why new? Because engineers, when you talk to them about Latin hypercube, filling space designs, in many cases, they have not heard of that. If you talk to them about Gaussian processes for modeling the performance of a system, they have not heard of that. If you tell them we want to use the sensor data through models to enhance monitoring, diagnostic, prognostic, and predictive analytics, that has not been usually considered. So that's why these are new engineering practices, and they are focused on performance. So by putting performance as a focal area, it generates a lot of impact on what you have to know and what you have to do. The digital twin is adding what we call chronology of time and goal, so the real-time aspect. So we need the monitoring to be real-time. We need the diagnostics to be real-time. We need the prognostics to be real-time. And if we want to get to prescriptive analytics, we need real-time optimization. This is a bridge between the engineering science domain and the statistical science domain. This last books, 221, 222, 223, we are trying to cover this bridge. The deployment, the delivery platform for the first book is JUMP and R, and there's a MyStat R package that you can download from CRAN that will do all the things I mentioned. These two books are sort of expansions of the first one here with Python, and there's a GitHub repository that will give you the ability to do all that with Python. So I have a few more minutes. What did I talk about? Mainly the journey to performance engineering. What do we see on this journey? We see emulators. So the Gaussian process is an emulator. It's a model that can be embedded in a digital twin. So instead of using the detailed FEM simulation or CFD simulation, we have an emulator or a stochastic emulator that can be part of a digital twin. This allows us for online analysis. We focus on the information. I have another talk on information quality. It is not this talk, but you will find it easily through Google. And analytics is definitely part of that. This means that the bridge between people who are experts in analytics and experts in engineering or mechanical engineering, my experience is that the most advanced engineering disciplines that touch on these areas are the mechanical engineers disciplines. Need to be this bridge needs to be reinforced in order to have this journey become a successful journey. So I'm leaving a lot of time for discussion. I hope there will be some questions and follow-up discussions. I understand Marcus will collect these from the chat. I see there are some questions on the chat. If people want to open up the camera and talk directly, it's okay, also okay with me. Thank you.
Great. Thank you very much, Professor Kenett. Yeah, like you said, if anybody would like to pop up their video and chat, please do. Just be aware that it is recorded. So if that, just so that you're aware before you pop your video on. Whilst we wait for people to maybe type in some questions, I've got one or two myself. So on slide 40, you talked about I think it's maybe a couple of slides back. Yeah, talked about this was really interesting about how you have optimal versus robust in terms of your stochasticity measures.
Yes.
And how you can yes, it might be optimal, but you can easily stray away. What sort of scenarios would you? I guess often you want robust, but is it like? Do you have any knowledge or opinion on what sort of scenarios you would want optimal versus robust measures?
Okay, so the basic scenario is to introduce uncertainty in the inputs. You see these green distributions?
Mm-hmm.
They are representing variability in K. K is the string coefficient. Okay, we have the value. We set the value in the experiment, but when it's going to happen in the system, the live system, it's not going to be exactly what we have set up. There's going to be uncertainty in there. So the green is giving us the ability to introduce uncertainty in the inputs. Now, this is the basic scenario where you put these uncertainties as independent. You can get more sophisticated and introduce some multivariate structure in these dependencies. And then you can really go to, so now you move to, so here I'm on a univariate dimension. Each dimension is treated univariately. I can treat this as a multivariate space problem. And then I can generate points with uncertainty in this multivariate space. The difficulty is you can justify the univariate uncertainty. It's becoming more and more difficult to justify the multivariate uncertainty.
Mm-hmm.
But in principle, it's doable. So these are data-driven scenarios. Okay, these are data-driven scenarios.
Mm-hmm. Okay, and then with this again on the optimal versus robust, if we often want a robust one, does that drive potentially just the use of, do we just go one step further and do like the second order modes of the distribution? Because then that gives us again a decent measure of the robustness essentially. Is there ever systems that use that instead, or do we usually still just use the first order and then sort of make like a qualitative decision on it?
So if you introduce this uncertainty, you can draw the uncertainty into the model, and now you have another model, which is a model of the variability. So it's not qualitative. You now optimize both on the performance with its targets and on the variability, which you want to be as low as possible.
Mm-hmm.
So if you combine the optimization so that the performance is on target and the variability is minimized, then what you're getting is prescriptive analytics. Now you have something to recommend on how to set up the system.
Mm-hmm.
And if it's done with the stochastic emulator, this can be done online as the system is running. You don't have to do it offline. You can actually do it live, online. So you can address situations that have not been envisaged before.
Okay,
the system can be in a state that no one imagined possible before, but it's setting up how to continue you can include these considerations online.
Okay. Yeah. And but is that always driven towards the optimal solution, or do you ever drive it towards the robust solution in terms of the optimization?
So you can say, I want to focus on the optimization, and that's effort 1. You can say, I want to focus on robustness. That's effort 2. Effort 2 is bigger than effort 1.
Yeah. Okay. We have some questions in the Q&A box. So Camilo asks, digital twins can be used as a tuning platform for PID gains in a process plant controlled by classical PID controllers with PLCs, or to test different kind of controllers. They're asking if, sorry, let me just, somebody is.
So this is touching on the discussion between statistical process control and engineering control. There's a discussion that is trying to balance an approach based on statistical process control, which is entirely data driven, and the discussion which is on engineering control, which is accounting for what you know about the system and the controllers affecting the system. So depending on where you are, if the controllers are well developed, then you are probably, the balance is probably on the engineering side. If the controllers are not well developed, then you are probably on the statistical side. So I think these are two options that you have to consider. What is the right balance? So the statistical process control eventually, if you have controllers, can work on the residuals, can work on the leftover variability, whatever is left over after you've done your best with the controllers. What is left off? Where to put your money depends on where the balance is. I don't know if it's the answer that Camilo was looking for.
Okay, great, thank you. Hopefully, I hope that
some engineers will say, you mentioned monitoring, and we are doing that with PIDs. We are introducing controllers. This is part of our toolkit. We know how to do that. Okay, we want to do it better.
Great, thank you. Hopefully that answers your question, Camilo. If you have any more questions, please do type them in. And now Graham West also asks, oops, sorry, I accidentally got rid of it. He said, thank you for your talk, very interesting. Maybe I missed a point, but at the end, you seem to suggest a need for real-time, for real-time, for the diagnostic and prognostic aspects, as well as the monitoring. Could you elaborate further on the need for the real-time, could you elaborate further on the need for real-time diagnostics and predictions aspects over just the monitoring? As he says, for many engineering systems, the degradation mechanisms are slow, and for diagnostics and predictive analytics, timely but offline timescale usually suffice.
Yeah, so first of all, thank you for the question. Actually, I was hoping to have that question. The diagnostics can be shared between offline diagnostics and online diagnostics. So I showed you the impact of V naught and K. Okay, this impact we can do offline. This is something we can learn offline. In the real system, as things actually happen, we can start from there. So the diagnostic has a knowledge base that can be developed offline and incorporated in an online system. So here we know how K and V naught affect cycle time. Okay. Given the situation that we have now, maybe it will affect it differently. We can do this online diagnostics that expands the offline diagnostics that we have. So yes, degradation is slow. We have degradation models. We can use them, but then we can also figure out if maybe things are not working according to these models, and we can maybe adapt the models to this specific situation. So the answer is a mix. Yeah, right. Offline is really important. The question is, can we combine offline and online? And my answer is yes, we can do that.
Great, thank you very much. I also have one more question for you. So whenever one, either a researcher or practitioner or anybody selects these models, be them black box machine learning models, physics models, or physics enhanced or informed models, then whenever you select these, you embed some sort of belief, whether be it the type of belief or the level of belief. Do you have any sort of thoughts or opinions on any of the things that you presented here, and when you should use them based on what belief you have of your system? For instance, is there any sort of models that are often used with an incorrect belief, do you think, or where we can improve certain beliefs?
Yeah, so
quite an open-ended question, but
yeah, no, I would treat this question not so much in terms of belief, but in terms of validation or certification. I mean, it's not an issue of principles. It's an issue of extent. You know, the Gaussian process model is very general. It has computational issues when once it becomes very big. We might want to do some blocking. People do some blocking for parallel computing to use this type of models. So which of these, if you do that, then you're getting local optimizations as opposed to global. So what is the thing to do? If you certify the performance and you know the difference, you're okay. So the belief is not an issue of principle. I think it's a technical issue that should be tackled by validation methods. You need to have good validation methods. Once you use neural networks, okay, we're going to have training systems and validation systems. Can the validation data that we use generalize to the real situation? Depends on the data. You know, maybe when we developed the neural network, we had situation A. When we split the data into training and validation, and then we tested the validation in situation A, we were doing very well. Maybe now we're in situation B, and this maybe has to be redone. This is entirely different. So it's not a matter of belief, it's a matter of knowledge. Do we know how much the discrepancies? Do we know how good the model has been validated? I would not put it in the context of beliefs, because beliefs, this is an endless argument that cannot be closed. You know, it's an open argument. As you said, it's an open argument. Why is it an open argument? It's an engineering argument. It's a technical argument. We should be able to close this argument technically.
Yeah, that makes sense. I suppose it's because it gets quite strong onto the when you start to say, okay, I believe that this model is formed from this, then you are, by saying that, it is a technical argument. So I
Yeah,
see what you
so
mean.
I know you
Yeah.
have some I know Sheffield, I know the Bayesian O'Hagan, and this Sheffield is known for Bayesian Bayesian preference, right?
Mm-hmm.
I think you have to be a practical Bayesian. You know, the way to do this, I think, is sort of halfway. You know, if you are going all the way and you talk about beliefs in a Bayesian context, I think you will have difficulty meeting reality. That's my
Mm-hmm.
opinion.
Yeah, I suppose I was more talking like there's like one belief that you automatically embed whenever you have, let's say you have a neural network and you say you use a certain measure as an input and a certain target as the output. You have a
Yeah,
belief that there is a function that is described from that input to that output, right?
yeah,
So not necessarily in terms of stochastic beliefs or anything like that, but more like, I believe that there is a description that can go from here to there. Um, but then
yeah.
once you're doing that, like you said, that becomes a technical description rather than a belief.
That's what I'm saying. So what you're talking about should be now specified in details and verified for
Hmm.
this locomotive system, the brake system. Let's do it for this brake system. You
Hmm.
know, I tend not to see the value in the general discussion. There's not going to be a one answer for all. That's
Hmm.
that's maybe the assumption here. And because we have all these capabilities now, both analytic and with sensors, you know, we are so rich in flexibility. We should use that. When we did not have these capabilities, we needed to simplify things. We don't need to simplify things anymore.
Yeah, that makes sense. Do you think there's a danger of over exploiting capabilities of new algorithm techniques? Or...
So another point we have not this is not something that we raised here. People push for, we want automated answers, we want automated solutions. I have goosebumps when people say that. I feel very bad about that. You know, you cannot have automated. You need to leave some room for some understanding that comes from experience, intuition, etc., etc. So the engineer has to understand the system he's working on. This guy Gabriel Davidian, I'm working with, he's the head maintenance. He's in charge of maintenance for the railway. He knows these systems intimately. He knows them, by number. He knows the difference between I-55 and I-62.
Mm.
You need to spend time to get some knowledge like that if you want to do a good job.
Okay. So you think by allowing the freedom in this, like by not over prescribing in terms of reducing it to assumptions, we create room to allow these intuitions to develop essentially.
Right. Um, a famous statistician, Cuthbert Daniel, used to say, you can observe a lot by looking.
Yeah.
The problem is the oversell of deep learning. You know, people say, if you have enough data, we will solve all the problems of the world for you. To me, this is overselling.
Mm.
We can do better. We can do better by having less anticipation of what deep learning can provide. Deep learning for image processing, okay. But you know, for this type of systems with so much variability in so many inputs, it's very useful. I'm using it, but there are limitations. That's why I called this open-ended issues porous systems. We have porous systems. Things will happen that nobody anticipated. The user will use our system in ways that nobody had anticipated when the system was designed. But we still want it to work. We don't want to have an excuse, oh, you did not use it properly, that's why it broke. Not acceptable.
Yeah, no, that makes sense. No, that was very interesting insight. As we're, in fact, over time, I'd like to thank you again, Professor Kenett, for the talk. It was really, really interesting. And I'd like to thank everybody who attended and for the questions. And yeah, so thank you again for your time. And before everybody goes, I'd just like to note we're hosting another webinar again soon. So do check out the DCE either on Twitter or on LinkedIn for any updates on both these webinars, any papers, anything like that, and any more discussions as well. So one last time, thank you very much for attending, and thank you very much, Professor Kenett.
Thank you very much. Bye-bye.